presenting to you a paper titled Deep Learning for Lithium Battery Management System. It's a systematic literature review. I'm happy to be here and thank you so much for the opportunity. So from the we can get it on. From the first slide, we can actually see the authors, the title of the paper, and we are from the Computer Systems Engineering Department at Tshwane University of Technology here in Pretoria, South Africa. So yeah, let's get on. So the agenda that I'm just going to be focusing on in regards to this presentation, I'm just going to talk about the overview of the presentation, the introduction, and also importance of battery management systems. I will talk about the evolution of battery management systems techniques, a research questions and methodology, search and selection process that was carried out. We'll then move on to the key findings while just addressing all the research questions that were raised at the beginning of the systematic literature review and the challenges in the implementation. Um, yeah, that is on the research question number 3. Also look at the gaps and the challenges for and future directions. Then we move on to the conclusion. So yeah, we move on to the next slide. So with the advent or the rapid electrification of transport and domestic use, or the incessant need for energy, for sustainable energy, uh, lithium batteries have become one of the most important power sources to be used because of their because they are very good in the way they handle power storage, and because of this there exists a need to be able to then get or design battery management systems that are able to to monitor the way in which the lithium batteries operate, charging, discharging, so that safety and also range of the lithium batteries is also maintained. So it is because of this that we have actually realized the need to actually just have a look at how we can actually implement or the role of these battery management systems to in the applications of lithium batteries. So one of the the challenges with lithium batteries is their behavior is dynamic, meaning that it's non-linear in nature in which they operate. So it then becomes a challenge to be able to really map out the temperature or load variations. That's because obviously we're using a battery, we need to be able to know the state of charge and state of health of the battery. But because of this non-linearity, it becomes so difficult to be able to really accurately estimate the state of charge and state of health. And thus also it because of this it can cause problems such as thermal runaways or inefficiencies, but in the operation of the battery. So it is really necessary that we have a way to map out these relationships in a lithium battery. Yeah. So in terms of battery management systems, basically there is in the early designs, like that is from the 1990s to 2010s, uh, basically battery management systems, or majority of them, they use rule-based methods to for SOC estimation and state of the art estimation. uh, these methods were pretty simple, but the problem is this method didn't really have a way to really model or map out the dynamic nature in the conditions or when the lithium battery or the batteries are operating. But they were quite good to a certain extent, but the state of charge estimation was very bad, leading to errors of around 5 to 10%, which is, yeah, which I still think was there was quite room for improvement. Then in the 2010s, we moved on to the statistical machine learning, e.g., the Bayesian and the support vector machines. These improved in terms of SOC estimation errors to from 3% to 5%. They were better at adaptability in terms of also mapping out the complex relationships between that existed between the temperature, voltage, and current of the lithium battery. But there was still more room for improvement. So from 2018, that's when we see now more advanced machine learning and or deep learning models being developed so that they can be able to accurately measure the state of charge of the batteries. These represented errors of somewhere below 1.5% in the estimation, state of charge estimation or state of the estimation. So these are the types of studies that the systematic literature review really honed in on. Um, so, in terms of the research gaps and SLR and motivation, so the majority of from the SLR, what I found is the majority of the studies focus mostly on just a single aspect of battery management, like state of charge estimation, and then it then leaves out the other aspects. Let's say fault diagnosis, or 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 fault detection on the battery. So it is because of this again, that is because you want ideally a battery management system is supposed to be able to 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 have a fault diagnosis. So it's supposed to have fault detection, supposed to have state of charge, state of health of the battery all in one. But the models mostly were more focused on state of charge and some of them state of health. But for diagnosis, I found it to be quite challenging to find studies that had developed models, AI models for diagnosis. So the aim of this systematic literature review was to synthesize in deep learning and BMS for state estimation, fault diagnosis, and be able to also address the issue of optimization. That is when we want these models to be deployed on embedded systems like microcontrollers. So yeah, that is another area that the SLR focuses on as well. Moving on to the research questions. So it says, how do deep learning techniques enhance state of charge or state of health accuracy in BMS on resource constrained embedded systems? How effective are deep learning models for diagnosis challenges, solutions for deep learning on microcontrollers versus cloud AI performance, in terms of performance, latency, or power? Um, so the methodology will use the PRISMA networks framework. So the PRISMA framework, we used it to be able to select the studies that we really were really closely meshed to our study. So that is that, and then the search terms that we used in the libraries, battery management system, deep learning, machine learning, state of health, state of charge for diagnosis and optimization. Mainly the databases I focused on was the IEEE Xplore and the Scopus, and also in terms of the in terms of the studies chosen. First, it was 2010 to 2025, then filtered more to 2018, after 2018 for more recency. So the total studies were 9,803. Uh, Looking at the table shows the number of results that came from the search. Up to then we move on to the selection process. So in the primary process we remove duplicates and irrelevant studies. We screen in terms of BMS, battery management system, or AI focus, because we wanted more studies on BMS that were AI focused. And then also we used English language as a exclusion criterion, peer reviews as an exclusion criterion, and also recency, as I had earlier alluded to. Also in the second screening, we looked at studies that were more on the embedded systems side, to see studies which also talked about embedded systems. Also, keyword matches more like SOC and deep learning as well, and also practical implementation. We didn't want studies that were only scientific. We wanted studies where there was some practical done after research as well. So the final number of studies that we had was 52. Um, so as I had alluded to, this is the inclusion and exclusion criteria. Um, So, in terms of the key findings in the state estimation, this is what we found, that 80% of the studies were on a state estimation, 60% used deep learning. So, which is exactly goes to the point that most of the studies were more focused on state estimation of AI implementation in state estimation. We'll find out again when we go to the research question 2 that the fault diagnosis is not very much used, should I say. So yeah, that is another issue that we found there. Uh, so research question 1 so we also looked at feasibility of a resource of implementation and resource constrained systems, which are embedded systems, basically microcontrollers. And then in some of the studies, we found that yeah, they did manage to deploy an LSTM model on FPGAs, and the FPGAs are able to actually accelerate these models using low power and be able to have much more speed. And then deployment, it is possible, but it there is also some trade-offs that needs to be looked at when you're deploying on a microcontrollers. Like, obviously there is some optimization that is needed on AI models to be able to run on a microcontrollers, but that has a bit of an effect on the accuracy of the model itself. So it is then a trade-off between the this model size and the accuracy as well. So yeah, implementation is challenges. That is obviously deep learning models are quite complex. That and they are heavy in terms of computation. So on microcontrollers, in compared to cloud, whereby we deploy a deep learning model to the cloud and it runs on the cloud and it does all the calculations. But the good thing with a locally running deep learning model on a microcontroller is that you have decisions being made locally without any latency or relying on any network availability. So that is a good thing there. But obviously they are the ones that are deployed on microcontrollers are kind of watered down. That has an effect on accuracy as well, which is an advantage on the cloud side. Um, it is possible to actually deploy deep learning models on microcontrollers, but obviously it will really require quite huge optimization to be able to deploy on resource constrained embedded systems. So overall outcomes and gaps, strength. So deep learning does boost accuracy um, of state of charge estimation 1 to 2%. It is quite scalable to embedded systems via hybrid or lightweight models. That's basically we need to optimize these models to be able to then deploy them. The gaps that we found mostly were in the folds and optimization, because this field was underexplored. Like it is difficult to really standardize metrics in terms of how you measure fault diagnosis or fault detection in battery management systems. Um, there were like 3 to 7 studies that were more scientific in nature, with no practicals really done in that addressed fault diagnosis. So it is something that is still has a gap in terms of battery management systems. So that is one of the gaps that we found. And then future work and opportunities. Obviously, there is need to then have a way of standardizing metrics to be able to have for diagnosis done. Also, there's need when once we there's more on the deployment of AI models on microcontrollers, there is need to have security be apt to be able to reduce cyber attacks or to address that issue, and also to have BMS systems that has AI models running estimation for diagnosis, and also that are optimized to be able to run on a microcontroller or on any embedded system. So also innovations that can come, we can reinforcement learning can be used for adaptive charging, and also real world data sets can be used for validation and making sure that everything is working quite well. The broader impact of that is it will help in terms of global electrification and or grid stability. In terms of conclusion, deep learning revolutionizes battery management systems. It is superior in terms when we are estimating state of charge instead of health. Also, it helps in fault detection, but even though there is still a gap there, and then it is viable to really have a way of um, deploying them there on embedded systems. It contributes, and it really contributes to electrical vehicles, renewable safety and efficiency. So that is the conclusion. Then, in terms of myself as a presenter, my name is Raymond Mango. I'm a field application engineer at RF Design in Cape Town, South Africa. I am currently working on an honors at TUT, Tshwane University of Technology, and those are my details. Thank you so much.